Okay, this will be lesson 2 of chapter 9. So we're going to continue taking a look at the geometries of molecules, but here we're going to take a look at expanded octets, molecules that have more than 8 electrons around them. And this will give us trigonal bipyramidal electron domains. So if you take a look, this is a case whenever we have 5 electron domains. If you were to try to draw a molecule, or say if you take 5 balloons and tie them at the center point, the balloons will arrange themselves in this way, giving you 2 possible angles. The atom or the balloon that's at the top and at the right will be situated 90 degrees away from one another, and the inside balloons will be situated 120. The inside we call the equatorial positions, as on the equator, and the top and the bottom we'll call the axial positions. So we will have 2 possibilities here. Again, recall this happens because of electron-electron repulsion, and we get ourselves these 2 angles, technically. So here, actually, this is an important point. It is important to see that the one of these positions is actually more crowded. Here it says that lone pairs always are placed in equatorial positions, and this is because the equatorial position is less crowded. One of these atoms is actually further away from all the others than one of these. One of these guys, you can say, is close to 3 atoms by 90 degrees. One of the central or equatorial positions is close to, again, 3, but this guy here, further apart, and 2 of these are a little closer. But the idea is the electron pair that's empty will go in the position that's further away from everything, and that in this case is an equatorial position. So in other words, if we have to put an electron pair, if one of these has to disappear and become an electron pair, then it'll go in the central position, not in the axial position. And we'll see as we go along here what this means. So these are the axial and equatorial positions. So if we have 5 electron domains, there are actually 4 possible shapes, and these get a little bit involved, so we'll go through these in detail here. If all 5 of them are bonding, if all of these are atoms, then you get yourself an interesting shape called trigonal bipyramidal. And the reason for this is you actually have a triangle in the middle. Here it is, and then you essentially create a pyramid going up, and then you create another pyramid going down. So you essentially have 2 pyramids, and it's getting a bit messy, is it not? But you technically have yourself an upper pyramid and a lower pyramid, and both of the pyramids are sharing a base, and that's why we call this trigonal bipyramidal. An example of this is PCl5. If 4 of them are bonding and 1 is non-bonding, then the lone pair, recall we just said, goes in the equatorial position in the middle here. What results is something called seesaw. A very interesting, this may create nostalgic thoughts of your young days as a little barefoot child playing in the sand, and this is a very appropriate picture to show us the seesaw arrangement. So technically you think of these 2 as bars of the seesaw, going back and forth is the idea. If 3 of them are bonding and 2 are non-bonding, then again the other electron pair, empty pair, will go on again an equatorial position since it's less crowded, further apart, and this gives you a T-shaped, and this is exactly what it looks like. This is a T essentially. And lastly, if you have 2 bonding domains and 3 non-bonding, the 3rd electron pair goes on the equatorial position, and you just get yourself a linear arrangement. Now this is the same linear arrangement essentially. It will look roughly the same as we've seen before. However, this one's different because of these 3 electron pairs. It comes from, if you take a look at xenon difluoride, you do have 2 fluorines on the outside. However, you get yourself an expanded octet, remember, around xenon. So these 3 are influencing the shape to be linear. This is a different linear than what we've seen before. So these are the 4 possibilities for a trigonal bipyramidal electron domain geometry. And then finally we're going to come to the last one, the most crowded. If you have yourself 6, if you tie 6 balloons together, you'll get yourself this strange shape. and then this is essentially the maximum possible for electrons. Beyond this, the atoms get pretty crowded, and it's really harder to fit 7 or even 8. Now, the reason for the name octahedral, don't confuse that with 6 electron domains, is because a three-dimensional figure with 8 sides is called an octahedron. So again, if you create, you have 1, 2, 3, you get essentially, and then there was one on the back as well. So you got 4 sides, and you also have 4 sides in the bottom. That's how they get the octahedral idea. The important principle here is that you got yourself 4 electron pairs situating in the center or on the equator, and then you have yourself one above and one below. So you also have equatorial, and you also have axial positions, but these equatorial and axial positions look a little different than the previous one. And again, when you have lone pairs, all positions here are actually equivalent. In all cases, you have yourself 90 degrees, 90-degree angles, even though it's drawn kind of like this, but because it's 3-dimension, in all cases here you have yourself 90 degrees. And because all these are 90 degrees, all of them are equivalent. It does not matter really where you put the lone pair. But if you have a second lone pair, then the second lone pair will go on the opposite side. So if this were a lone pair, then the other lone pair will go here, because lone pairs are the most repulsive, and they go on opposite sides. And the reason lone pairs are most repulsive is because they take up a little more room than bonding pairs, as we'll see. So 3 possibilities for an electron domain geometry with 6 electron domains. And the first is if all 6 of them are bonding, then you get yourself this octahedral shape we just talked about. Spread the 6 balloons out in 3-dimensional space as far as possible. Octahedron is what you get. If 5 of them are bonding and 1 is non-bonding, then this one, it doesn't really matter where you put it. In this case, they're all equivalent, but let's put it down here, and you get yourself something called square pyramidal. So you got a square base, and you got yourself essentially a pyramid with a square base. That's kind of the idea. And lastly, if you have yourself 4 bonding domains and 2 of them are non-bonding, then the last or second non-bonding pair will go on the bottom on opposite sides, and you simply get yourself a square. And this square, 4 atoms lie in a plane, so we call this square planar. And these are the 3 possibles. Oh, this is a little strange, isn't it? This little R got a little subscripted. What a shame. Okay, so let's try 3 examples of this sort of thing. So it says go ahead and use the same Vesper theory to give the molecular geometries of these 3 molecules, NF3, SF4, and IF5. Let's, as we've done before, go ahead and draw the lowest structure of these. So we have NF3 to begin. Each nitrogen brings with it 5 electrons. Each fluorine 7. We got 3 fluorines. Adding them up, we have 21 plus 5. We get 26. And having 26, we got ourselves a nitrogen in the middle, 3 fluorines around the outside, and we got ourselves 2, 4, 6. Let's put the rest around the outside: 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Now this is actually a picture that we've from a previous example, very similar. So let's take a look at the 2 possible geometries, the electron domain geometry and the molecular geometry. The electron domain geometry, it looks like we have 1, 2, 3, 4 electron domains. That corresponds to tetrahedral. Tetrahedral. Here should be an R. Tetrahedral. And then since 3 of them are bonding and 1 is non-bonding, then this one you can think pushes the rest of these down and creating essentially this sort of shape. And that is called, if you remember, trigonal pyramidal. That's a trigonal pyramidal arrangement. So this is actually an example, this is not an expanded octet. You have 8 electrons around nitrogen, not more than 8. Let's do the same thing with the next one. The next one is SF4. Totaling the valence electrons, we get 6 from every sulfur. We have 7 from every fluorine. Multiply that by 4. 28 plus 6, you get yourself 34 valence electrons that we'll have to spread apart. So let's put sulfur in the middle, it being the less electronegative element. Let's put the fluorines around the outside. We got 8 so far. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 2 more to go, and the extras, recall, go on the central atom. So we have 34 electrons spread apart. And we do have an expanded octet in the middle there with sulfur. So we have, let's take a look at the electron domain geometry and the molecular geometry. The electron domain geometry, if you take a look, shows us having 1, 2, 3, 4, 5 electron domains, and that corresponds to trigonal bipyramidal. This is our first expanded octet shape, trigonal bipyramidal. And then 4 of these are bonding and 1 is non-bonding. And if you take 1 off, technically recall that you got yourself this sort of arrangement. And the electron pair, the extra electron pair, will go on the internal position, what's called the equatorial position. So you got yourself this seesaw shape, technically. So your seesaw, think of it, kind of looks like this. And then here's a friend, and here's you. Enjoying the seesaw as it goes down and as it goes up. Something like that. This is seesaw. Okay, and then let's finally take a look at our third molecule. That is the molecule IF5. Let's go ahead and total up the electrons possible. From iodine we get 7, from each fluorine we get 7. There are 5 fluorines, 35 plus 7. Looks like we got ourselves 42. That's quite a bit. 42 electrons. Let's go ahead and put iodine in the middle. And then automatically we'll have to put 5 fluorines around the iodine. So right away we'll begin with an expanded octet. Let's go and count the total number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. And then the final pair, we have 42, 2 more to go. Again, will go on the central atom. So iodine will have definitely an expanded octet with 12 electrons around it, which is possible for iodine. It being a big atom, further down the periodic table, it can handle this many atoms around it, or this many electron domains. So let's take again a look at the electron domain geometry, and then we'll take a look at the molecular geometry. The electron domain geometry is based on simply how many electron domains we have. 1, 2, 3, 4, 5, 6. That corresponds to octahedral. An octahedron, recall, is a shape that has 8 sides. And then only one of these is non-bonding. So the octahedral, if you recall, we had this sort of picture. The non-bonding pair doesn't really matter where it goes. It's easiest to visualize it going on the bottom here. And what's left, what you have left, is you have a square with a base that's, or you have a pyramid with a base that's square. That's called square pyramidal. So the molecular geometry is square pyramidal. So hopefully you enjoy these 3, and we'll do a few more in class as we go along. Last thing we're going to mention is some special bonding angles that happen whenever you have a non-bonding pair. So, because non-bonding pairs are larger than bonding pairs, and this is due to the fact that a bonding pair is shared between two nuclei, so it's spread out between two atoms, and it takes up less space. A non-bonding pair is not shared between two atoms, so it's able to spread out. It's on the outside of the atom. It's able to spread out more, if you would. This means there is more repulsion happening from these non-bonded pairs. So usually in a tetrahedral arrangement, you'll see 109.5 as the bond angles. But if one of these is a non-bonding pair, then this non-bonding pair expands, if you would, a little more, creating more repulsion and decreasing the bond angle, tightening the hydrogens up a little bit. If you have two of these, then these two essentially create even more electron pair repulsion, and getting it down to 104.5. So it's a good idea to remember some of these alternate angles. Really, oftentimes we just put less than 109.5, but it's a good idea to take a look and recognize that the bond angles will be a little less. A similar thing happens if you have a double bond. A double bond representing 4 electrons actually puts a more electron density, so you have a greater electron density in a double bond. And if the double bond is fixed, this is not a case in which there is resonance. There's actually no resonance here. So if you have resonance, then all 3 of these bonds, recall, will be equal. But if you don't have a resonance, and you don't have resonance because this oxygen is a different atom than this chlorine, so we cannot swap double bonds. If that's the case, then the double bond will create more repulsion here, and as it creates more repulsion, it pushes these 2 chlorines a little bit closer together and expanding the 120 to about 124.3, and then contracting this side to 111. This has also been verified for these sorts of molecules. And then it's a good idea to take a look at a molecule that has combined electron domains. In fact, in a molecule that's big, a large molecule, we can talk about the geometry around each atom, around the carbon, around this carbon, and around this oxygen. So if you take a look, this first carbon has around it 1, 2, 3, 4 electron domains that corresponds to being tetrahedral, because all 4 of these have atoms at the end of them. The carbon, the next carbon has, we can put this in a different color, 1, 2, 3 electron domains around it. 3 electron domains. If all 3 of them are bonded to atoms, this corresponds to trigonal planar. And then if you have yourself an arrangement like we have around this oxygen, let's pick a nice purple color, lavender. We have 1, 2, 3, 4 electron domains. 2 of them are bonding, and this essentially, these 2 non-bonding domains will push the other 2 down, creating this bent shape. Now, in terms of bond angles, we don't really care about the molecular geometry. We'll always take a look at the electron domain geometry, because the electron domains are the ones that are creating the maximal repulsion. So, to take a look at the bond angles, we have 109.5 in both these cases, in both the case of carbon and oxygen, because in both cases you have 4 electron domains, and then 120 in the middle carbon here, because the middle carbon has 3 of these electron domains. Now it'll be, as we've talked, this angle here will be a little less, a little more, this one will be a little more than 120 degrees. Whoops. And this one here will be a little less than 120 degrees, as we just spoke. And this should conclude, we'll do polarity next time, this should conclude lesson 2 of chapter 9.